story short, you got a plane trying to go this way, you got a wind pushing
That way.
from another way. And actually, to be honest, does it say blowing to the southwest or blowing from the southwest? My arrow's going the wrong way. Anybody and everybody with this picture, real quick. That's blowing to the southwest. He's blowing from the southwest. There we go. Is that better? From the southwest? Now, I went ahead and reminded you guys, even though this problem shows bearing, I say don't worry about bearings. I'm showing them to you because in physics they are going to be present. I'm trying to introduce some physics things in this chapter, but I went ahead and wrote the angles for you, and on the test I would as well. I wrote the angles for you in standard position, hence why we have this little 118, which is a little bit past 90. Probably should be up a bit more, but that's okay. Then we have this 215, which is in the third quadrant, so I gave you those angles. Don't worry about bearings in the sense of studying and examples, etc. So we have these two angles in standard position. We have a plane trying to fly, and we have a wind trying to blow. Well, it's not trying, it is blowing against the plane. Now, have you guys ever flown one direction, have it take a certain amount of time, and then fly another direction in the sense of going somewhere and coming back, and the times are totally different?
Yes.
Why is that true?
Because
Yeah, the wind makes a difference. If you're flying into the wind, aka it's blowing against you, what's that going to do to your time it takes you to get to your location? Yeah, it's going to take longer because the plane is still maybe going the exact same speed, but the wind is slowing it down, right? The instruments say it's going a certain speed, but how the problem says with respect to the ground, it's saying, okay, not according to the instruments in the plane, according to the outside of the plane. So that's what's going on after the wind affects it. Or if you're going with the wind, then you're going to go faster. And so your flight time is going to be a bit shorter because you were able to make or gain more distance with the same speed that the plane is trying to go. So, in this one, question, is the wind helping or hurting? Mostly hurting, yeah. It's kind of like broadsiding the plane. So it's going to slow it down. It's going to make it probably a little bit harder to steer, etc. You're going to have to work hard to keep it on course. Well, the instruments are going to work hard, but so are the people in the cockpit. But then coming back, what was I doing down below, kiddos, when I started writing P equals for plane and W equals for wind? What kind of form was I putting them into? Component form. Good. Where on earth did I get these formulas? Why was I using cosines and sines? That is a formula for A and B. A equals magnitude cosine angle, B equals magnitude sine angle. So all I had to do was steal stuff from the problem, like the plane is trying to go, the jet I should say, but whatever, the plane is trying to go 580 miles per hour, that's the magnitude. Its angle was 118 degrees, so I stole that. The wind, it said from the southwest. I probably wouldn't give you guys one that's this tricky either. Wait, what's 180 plus 45? I'm struggle. I can't add. That should have been 215. What should that have been? Yeah, if it was perfectly in the middle, they didn't tell us a specific angle. They just said from the southwest. Let's change those really quickly to 225s. I'm sorry, guys. Unit circle fail on that one. Addition fail. Either way. Oh, that's still green. So 225. Once again, that angle would be given to you. You guys wouldn't have to figure it out. How do we put two vectors together? So let's see. Letter A was draw a picture, check. Letter B was write the velocity of the wind, W, as a vector, got it. Write the velocity of the jet plane, got it, in component form. Letter D says, what is the speed of the jet with respect to the ground? They want the overall result, aka P plus W in the magnitude, because the magnitude in this problem is the speed. If you look up here, this magnitude was speed, this magnitude was speed, so we need to find the magnitude of the sum. How do we always add vectors, cool kids? Just add them. Horizontal plus horizontal, vertical plus vertical. So what am I doing right now in my calculator? Thank you, Sam, that I'm plugging in. 580, yep. 118 plus 60 cosine 118. I'm adding both the cosine, not 118, 225. I'm adding both the cosine components. I'm getting negative. Someone double check me, make sure I'm good. 314.7199. Remember, don't round until the end. Anybody back me up on the, okay, good. Horizontal one matches. Let's try the vertical one. Remember, we're adding 60 sine of 225. As you guys can tell from the problem we've been doing, a calculator is going to be very important on this next test. 6, 8, 3, ... No, they're very important. Like, you're going to have it the whole time? Yeah, the whole time. Chapter 6 was all calculator stuff. Wait, but I need magnitude! I have components, that's great and all, but what is the speed? They want the magnitude. Well, how do I do that? Yeah, why am I doing a square root? Because I need to use my formula. And my formula says take A and square. If you want to, we can think about him as A and think about him as B, right? Just do A squared plus B squared. I'm doing that because my calculator is going to do all the work. I don't need to write all these numbers again. I'm going to use my calculator to do a big old square root of, go steal the negative 314. Make sure you put them in parentheses though when you square them, or else the negative times a negative will not change to a positive and you'll be in some big trouble. Put these numbers in parentheses before you square them under the square root. Someone double check me. What I'm getting is 565.377. I didn't round, so you should all have the same number. Of course, like all good math and budding physics students, maybe.
Parentheses.
But units. But yeah, parentheses are the math student, and then units, miles per hour. And that is letter D. Anybody back me up? Nice calculators. Yes, and then this. Thanks. What's the very last part of this problem?
What is the true direction?
Direction? How do we figure out direction? Oh, true direction. So not what the plane is trying to do. It's getting thrown off course a bit with the wind. But what is the true direction? What is the angle? Did you guys see that I wrote it? What is the angle of the sun? Well, how do I find angle? Magnitude. I do that whole square rooty thing of a squared plus b squared. How do I find angle? And not just tangent. Well, okay, you can say tangent. Sorry, I'm moving the picture. You can say tangent of the true angle without even having to draw any of this craziness and translate and do the vector diagrams and all that stuff. We can say tangent is going to equal b over a that we found down here with our sun. And that's the formula. Actually, technically, how does the formula go? As far as us solving, theta is equal to, yeah, I need to get tangent to the other side, so take tangent inverse of both sides. We have those numbers still stored in our calculators, right? We've been solving. So we're going to go steal those numbers, and I'm going to do second tangent. I'm in degree mode. Hopefully you are too. B is the 469-ish one, over A, which is the negative 314-ish one, and I end up with, oh, this makes total sense, right? Theta equals negative 56 degrees, 0.175. Doesn't that make tons of sense, guys? The plane's going this way. Wow, that's a strong wind. Wait, what? The plane's going that way. How is the plane all of a sudden going this way? Use your logic.
It's the negative thing.
Yeah, remember we talked about, was it Thursday or Friday? I forget which one. We were talking about how the math can only get us so far. And so the math says, oh, hey, he's going this way. But your logic is like, no, he's not. What's wrong with you, right? How can we use, no, the pilot doesn't stop. How do we use the math to say, okay, fine, math, you tell me that he's going this way, but I can use my logic to actually get to the angle where I want it to be. Plus 180. Now technically, guys, this would be a little bit off if I was to do my vector diagram. We would shift our wind up here just a bit. It's actually pretty tiny. And then we would have our resultant right here. This would be the P plus W. So I was making up the angle just a bit. Technically, it would look a little bit more like this. But once again, you guys don't need the snazzy vector diagram to know if I have this angle that is not at all where my plane is trying to head. So since I'm trying to get to the second quadrant, I have the fourth quadrant. Without even having to draw a lot of stuff, you can say, you know what, all I need to do is not everyone, some of you have already said it. How do I fix it?
Plus 180.
Need to add 180. Remember in our notes? With tangent inverse, sometimes we have to add 180. And sometimes we have to add 360 to make it a proper angle. So we can use the math, add our 180, and I think we end up with 123. 0.825. That's 60 minutes if we got to at least get an accurate answer. And then E is done. Okay, long story short. A lot going on. But a lot of this, let me get my mouse out. A lot of this is reviewing things that we've already done, like how to get a vector into his components from a magnitude and direction. We tried to practice that twice. How to find the result, or the net force, net speed in this case, the resultant speed. In components, easy math, add them down. But how do we use that easy math in order to get magnitude and direction? Well, we have to use our formulas of taking the A and the B, squaring them, adding them, square rooting them for magnitude, Pythagorean theorem, ultimately. And taking tangent inverse of B over A in order to get an angle, which is great, unless the math says, hey, he's going this way, and it's opposite. We have to add the 180. Once again, math has its own limitations. We have to still keep our logic. Hence why the argument, I have a little calculator app on my phone, why do I ever need to take a math class? Does not go either effort. Life is more complicated than a little calculator on your phone. And not just for tip. Okay, so, although there are tip calculators too. Don't you guys double the tax? If you say you don't tip, you're a horrible person. Okay.
What is that? That's like 20%. That's crazy.
That's actually really nice. Unless you don't like the person, then you can do like
What if
1.5
they're awful?
times.
I'm not giving them. If the
One
person
half
sucks,
percent? Okay, that's
they should have been better.
Once you guys start getting jobs in food service, you'll be much more sympathetic. Hopefully. Kiddos, you guys have, that's not your assignment. I think it's a little different than that, isn't it?
We're not on 6.1.
Let's see.
Oh.
You guys know where to find your homework. It's online. We're good. We're going to section 6.4, but before we do, number one, 6.4 is faster. It's newer. No, vectors were new. Vectors were new. It's shorter, number one. The homework is shorter as well, number two, which we're going to appreciate. So the section is shorter, the homework is shorter as well. You guys are starting to frantically write, but hold on, give me 1 second. Where are we at? 6.4 is going to take a day. I'm going to do a little bit tomorrow if we need it. We probably won't need it, but just in case. 6.5 will do almost 2 days, because we're just doing a little bit of 6.4 here today. 6.5 will be done with by Wednesday. So kiddos, we're just going to bust it through, review, and test. Now, listen carefully. Listen carefully. Listen carefully. We do have some homeworks that are kind of boom, boom, boom in the sense of I have right now that 6.3 should have been fully attempted today. Hopefully it was. I told you that on Friday. We're going to check it tomorrow because we just went over that last word problem today. So we'll check our answers on 6.3 tomorrow. Section 6.4, you could probably do most of it, if not all of it, tonight, but I am leaving a little bit of room because your test corrections are supposed to be due, I think, today, but who remembers on a Monday? Let's just turn them in tomorrow. As soon as you get in here tomorrow, staple those corrections to the front. Get them turned into your folder in the back. So then we'll make 6.4 due on Wednesday, 6.5 due on Thursday. Oh, you did right, it's 6.5 due on Thursday. Here's something you should know about the test. Number one. I told you from section 6.3, the big nasty one, there's only going to be one word problem. It's like one of the examples, the 3 examples we did in class. Number 2, you're going to see there are a lot of formulas in chapter 6. We have 6.1, law of sines, and an area formula. 6.2, law of cosines, and an area formula. 6.3, all the vector formulas. 6.4, a couple more formulas. And 6.5, a few more. Now, this was physics. Even then, some physics teachers these days just give you formula sheets.
I like
If it was physics, I would see maybe a reason to make you guys memorize all the formulas, but since it's not physics, I am not. Now listen carefully. You are allowed to make a formula card or even a sheet, like a half sheet of paper. Don't do a full sheet, that's silly. You can do a formula card or even a half sheet of paper because you are allowed to do any/all of the formulas from 6.3 to 6.5, meaning anything to do with physicsy vectors from 6.3 or 6.4 or 6.5. Any of those formulas are fine. So what are the only 4 formulas, the 4 categories of formulas that you have to memorize? Law of sines, law of cosines, area formula from 6.1, area formula from 6.2. You are not allowed to write any of those in your formula sheet/card for Friday. Okay? But other than that, you can write down any formulas from 6.3, 6.4, 6.5. So as you guys are doing homework on 6.3 and 6.4 and 6.5, just get that written down. Be using that sheet so you're used to it, kind of like you did last time. You only have to know for the test law of sines, law of cosines, area formula 1, area formula 2. That's another reason why it's better just to get it in this week so you guys don't have to memorize all those extra formulas like this one. This one can go in the card. And we're back. 6.4. So you need a working calculator for Friday, not a dying one. A living and active one. Okay, maybe not living, but at least active. And a formula or a half sheet, formula card or a half sheet. That's all the formulas. You hand write them down from 6.3, 6.4, 6.5. More involved operation in vectors. What? We've already done operations of vectors. We've added them, we've subtracted them, we've multiplied them by numbers. Whole numbers, fractions, negative numbers. What else could there be? Well, this guy. He's a pretty important one for physics. He's called the dot product. The reason why he's pretty important is because he is applied in lots of different formulas, and we're just going to see a few of them in 6.4. Once again, not ones that you need to memorize, but the ones that you should use. There are tons of properties down below, kiddos, but I'm just going to have you write 2 of them. If you've written more, that's great. But we're just going to star, hence you really, I think, only need to write 2 of them. Now, one quick thing I want to add to this formula is when you do what we call the dot product, you are multiplying 2 vectors together. Oh, check your notation. I can take off points on the test. Check your notation. Anything bold better have little vector arrows above. When you multiply 2 vectors, it is very different than multiplying a single vector by a scalar. A single vector by a scalar doesn't change direction unless it's multiplied by a negative. It maintains its vector status in the sense of having a magnitude and a direction. But when you multiply 2 vectors together, it's actually mostly useful as a tool to apply. So it does not solve for a vector. It solves for a constant, which is a little weird. So you guys have been doing a lot of math where if you start with a vector, you end with a vector. Maybe a different headed one, a different pointed one, a different length, but still a vector, not anymore. When you multiply 2 vectors together, you get a constant, which in physics we would call a scalar. Dimensionless, another way of saying it, it does not have direction. It is not a vector. The result is not a vector. And we have this super important formula that you guys wrote, but you might not fully comprehend. How do we find the dot product? And I'm not even going to really say U times V. Ew, gross. Because times you're going to think of doing this a completely different way. I'm going to say U dot v, or the dot product of u and v. Where do u1 and u2 come from? The a of u and the a of v. If I was to color code this, I could go ahead and make it, I don't know, something like, let's do something bright. The a of u, the a of v becomes u1, v1. So multiply the firsts, plus multiply the seconds. u2, v2, which is like the a, the v and the b of vector over u and vector v. Multiply those two, add them together, and you get your one constant. Okay? Now, before we get to practice with this, just a little bit, properties. You don't need to write them all. Let me show you which ones I think are the trickiest or the least intuitive. Number one, you guys are like, oh, I'm used to that. 2 times 3 is 3 times 2. Now, these are vectors, but it's still true. 0 times anybody is 0. These are vectors, but still true. Number 3, you can distribute. These are vectors, but still true. Number 4 is a little bit counterintuitive. It's based on this dot product idea that you're not used to. So 4 and 5 are the two that I would write down. And 5 is actually a really common algebra mistake. But just a few of you guys might mess up. So you can write them all if you would really like to. 4 and 5, I think, are the ones that are different. 4 says if you multiply a vector v by a vector v, it's the same thing as just squaring v's magnitude. Maybe that's an easier way of solving it. So technically you could say it's the same thing as the square root of. Instead of doing a and b, just because all of these vectors have their own a's and b's, the u's and the v's and the w's, I'm going to use the notation from above, which was v1 squared plus v2 squared. But if you square the magnitude, hold on, doesn't that square root just go away? So it's really just v1 squared plus v2 squared, if that helps. It's really just v1 squared plus v2 squared. And then number 5 is actually, yeah. Actually, the dot product. Because if you think about it, I'll show it down here. You guys don't have to write, I'm just illustrating real fast. If you have v equals v1 and v2, the dot product says you would multiply, just think about having v twice, sorry, vector v. So my color coding, multiply the first times the first, which would be v1 times v1 or v1 squared, plus the dot product says multiply the second ones, so v2 squared. Yeah, dot product is a little counterintuitive because you guys think multiplication, which this does utilize multiplication, but it still has to be within the bounds or the confines of how it's defined above. But number 5, sorry. Number 5 is the one that you guys, not you specifically, but you generally make mistakes on. We only distribute a constant when there is a sum or difference. We don't ever distribute a constant over multiplication or division. Powers, we might. Over multiplication and division. Actually, powers we can't over addition and subtraction. But constants are only allowed if it's multiplied by the dot product of u times v. He can either go to u or he can go to v. He will not go to both. And that's actually algebraic as well. It's one of those weaknesses, just some of us, I don't know, the bad habit that we brought from before. So if we had something like 3 times x squared y. Maybe you guys wouldn't think of doing it this way. Let's do something else. Let's do 3 times x squared times x plus 1. Just a couple of you, when trying to simplify this, would do 3x squared plus or minus or times or something. And then you would put the 3 again, and that is totally illegal. The 3 would either have to go to the x squared, or the 3 would need to go to the x plus 1. He could not, see, he can go across the addition, but he can't go across the multiplication. So anyway, all that to say, away with this dot product. Watch your notation. It just says examples at the top. Watch your notation. I have bold letters all over the place. He's a vector, he's a vector, he's a vector. Oh my goodness, these are linear combination forms. That's okay. That's okay. Whether they're in linear combination form or whether they're in component form, you deal with them the exact same way. If you like it better, you could always write a linear combination as or in components very easily. Just steal the coefficients, keeping them in order. If you want to rewrite them, you may, you don't have to. But using the formula from the page before, U dot V. We take, if you want the color coding, we take the first times the first, the coefficient. If the first times the first, if you want to think about it, the first times the first, and we end up with 4 times 1, which I know most of you can do mental math. I'm just showing the formula in action. Then we do second times second, that'd be a 1. Or second times second. We end up with 4 plus 2 is 6. It's a constant, and you're right. We're just practicing. How do you multiply one vector by another? You gotta use the dot product formula. First times first plus second times second. It's as easy as that. It's as easy as that. Now in the one down below, we gotta be careful with our math. Some of the homework might go a little crazy in the sense of, okay, we gotta keep track of these numbers. Let's go ahead and first think of what is V times U. Sorry, V dot U. Oh my goodness. Make a mistake, I said I wouldn't. V dot U. If it helps, let me circle these real quick. Just these two. V dot U. What do I do first in dot product? First times first? Is that alright? Need me to show it out? It'd be 3 times negative 4. First times first plus second times second. What would that be? 3 times 2 minus. That's technically V dot U. Double check it, make sure it makes sense. Did you guys just see me do U dot V? Didn't I do the left and then the right? Does that make a difference? Nope, the property says U dot V exactly. Is the same thing as V dot U. So no big deal. No big deal. You do it in either order. But what are they asking for next? V and W. So what's first times first for V and W? V1 times W1 or W1 times V1. And what is that in terms of numbers? Negative 4 and 3. Plus, and what's second times second? Look at the commas. Good. Second times second would be 2 and negative 1. And now, kiddos, the name of the game is PennDOT. Please excuse my dear Aunt Sally. Do grouping symbols first as much as you can, then multiplication, division from left to right, and addition and subtraction. So I kind of have grouping symbols, I suppose. So multiplication within the grouping symbols, negative 12 plus 6 minus negative 12 minus 2. Keep it legal. Watch out for bad math. Don't let it get you. The negative 12 plus 6 is negative 6 minus negative 14, right? Now we need to go ahead and say minus and negative, same thing as addition. Negative 6 plus 14 is? Dun, 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 dun. Keep it legal. The math might get a little funny, but you see how they're just having you practice with dot products? First times first, second times second, keeping it straight. Some of you guys that have wanted numbers for a while, there they are. you might be like, oh no, it's another formula that we don't need to memorize and you can put on your formula card. Well, that just got a little better, right? So why on earth are we looking at this formula in the dot product section? Oh. What do you guys see up top? Who is that? Dot
Oh,
product.
no.
Yeah, see it? So we're just giving you a peek. The book is giving you a peek. I'm giving you a peek by having you do just a few problems in this section, not a lot. I'm giving you a peek at how the dot product is useful. Now, some of you are going to be a little bit confused by this picture down here. Don't stress too much. Long story short, when you connect two vectors head to head, that is not the sum, that is the difference, because they're working against each other. So they're showing what happens when you connect the heads of two vectors. You do have this angle that's in between. If it helps you guys a little bit, they're kind of showing you the angle between two vectors can be kind of seen as a part of a triangle. That's all that picture is really for. The angle between. Before we would say, okay, fine, if we know this guy, that's a side. If we know this guy, that's a side. And we need another side or an angle or a, law of sines, law of cosines kind of breaks down because it's like, well, how do we find that theta thing in between? And the cool thing is with vectors, we don't have to worry about law of sines or law of cosines. We can just plug and chug to the formula up above. So in order to plug and chug, we got to find each of our pieces. So we have vector u and vector v. Do you guys get them down? Sorry, I'm kind of zoomed out. Vector u is 3, 2. Forget your notation. Vector v is 4, 0. For my formula, I need a few pieces. I need to know the dot product. I need to know the magnitude of u and the magnitude of v. So I'm going to go ahead and before plugging into the formula, I'm going to find each of those. What is the dot product? What is the magnitude of u? What is the magnitude of v? I'm going to find each of my pieces, then I'll plug in. My big old cosine of theta is equal to something. We'll get there. U dot v. Let's see if you guys can follow any faster than before. First times first. How are we doing? 3 times 4, right? First times first. Plus second times second. Which will just be 12. Because 2 times 0 cancels out, right?
Yes.
Cool. That 12, if you want to actually go in order, that is the numerator of my formula. The dot product goes up top. Magnitude. We practiced this earlier today in that example of the word problem, the plane and the wind. Do you remember how to take the components of a vector and get the magnitude? Yeah, we're not doing point to point. Some of you guys have done 6-3 and you had to figure out the components from like initial and terminal points. These aren't points, these are vectors. So I know you use horizontal, it's 3. I know you use vertical, that's 2. 3 is 9, 2 and squared is 4, 9 and 4 is 13. So we put rad 13 down below. Magnitude of v, take his components. 4 squared plus 0 squared. That's annoying. 16 plus 0 is 16. Square rooted is 4. How do we finish our formula? Well, I guess you could reduce a little bit. 12 and 4 is 1 and 3. But long story short, at the end of the day, to get to theta, what are we going to do to both sides, guys? Yeah, you're going to have to use cosine inverse, right? Get rid of that cosine. Theta is equal to cosine inverse of all that jazz.
33.690.
Just double checking so that we have it back up.
I can make it one.
33.690, that's what you got?
Just get enough money from gambling.
That we don't endorse. Okay, so 33.690 would be the final angle, and we didn't have to do any crazy geometry stuff or law of sines, cosine stuff, and you get to write this formula in your card, on your card. Now, kiddos, there is 2 more, and they're quick. 2 more applications to dot product that we'll see tomorrow. But the nice thing is you've learned the main new math from section 6.4. It's the dot product. we're just gonna learn 2 more quick applications tomorrow. So, tonight, finish up 6-3 if you have not yet. We'll check it first thing tomorrow, but you guys will be turning in your test corrections by the end of the day tomorrow. Corrections, stapled on. You guys still have 60 seconds. So we,
Yeah,
I
Ricky,
put
get
it on
over
this
here.
example written down. Bummer.
Sorry, Ricky, you're gonna be banned from the class.
That's okay. I still have 50 seconds. Guys, go ahead and grab a seat. You might not write it. I'll have it on the board tomorrow. You can write it down before we check 6-3. Sorry. Yeah.
Thanks.
It's okay. Excuse me then. Real fast. Okay. Orthogonal is a snazzy physics term, and all it means is what? That's it. 2 vectors are going to meet at a right angle. Wherever they are, wherever they're oriented, they're going to meet at a right angle wherever they are, wherever they're oriented. If their dot product is 0, which is a lot easier than figuring out whether or not the sides make a right triangle. My one that's looking at the clock, what a waste of time.
Darn.
So how would we figure out whether or not these ones below are orthogonal? Well, we're going to have to go to components. Most of you are more used to them. You can wait a couple more seconds. What would my components of the first one be? That's all I'm asking to let you guys know. Why 1 and 0, Nathan? You're saving your class.
Oh, right. The 0, there's no J.
There's no J, and then we're going to do dot product. Bye, cool kids. I'll see you tomorrow. Thanks, you guys too. It's chapel day.
Wait, does that mean that any vector that is... Oh, wait, never mind. Never mind. It was a dumb question.
Oh, it's okay?
Yeah.
Alright. Bye, guys. See you later.
Wish me luck, Miss D.
Uh-oh, look, what, bud?
What? Oh, hold on.
Oh, luck. You got this, buddy. Keep your formulas close.
Have a nice day.
You too.